Imagine this. You're walking across a bridge. Beneath you, a steel arch flexes ever so slightly. The wind whistles briskly between the cables. Somewhere in the distance, a bus rumbles like a drum, and the deck under your feet trembles just a little. For an ordinary person, these are just quirks of the structure. For an engineer, these are red flags. Bridges are creatures that live their own lives. They bend, vibrate, heat up, cool down, and sometimes behave in ways that calculations never predicted. We think of bridges as monumental and eternal. In reality, they are some of the most temperamental, complex, and dangerous structures ever built, and engineers often admit, if you want to tempt fate, build a bridge, but if you want to torment an engineer, make them responsible for one. Today, let's explore what makes bridges so dangerous, why engineers dread them, and which structures have gone down in history thanks to their collapse. Tacoma Narrows, the bridge that loved to dance too much. The story of Tacoma Narrows is practically engineering mythology. Opened in 1940, it was incredibly light, sleek, and modern, but that very lightness became its doom. Strong winds generated horizontal and vertical airflows along the span, and the bridge literally began to dance. At first, it seemed amusing. Locals even nicknamed it Galloping Gertie. But one day, the wind matched the bridge's natural frequency, triggering resonance. The entire span started twisting like a ribbon. Within hours, the bridge collapsed into the water below. This was the first time the world saw that aerodynamics could destroy even massive engineered structures. From that moment on, engineers have treated wind loads with near paranoia. In every bridge, they see a potential dancer. Wind doesn't just blow, it attacks. Bridges are tall, long, and flexible. They capture the wind's energy with alarming efficiency. On cable-stayed and suspension bridges, the cables generate Kármán vortices, small turbulence cycles that make the cables vibrate. Years of such oscillations can destroy fixtures. Sometimes, bridges even start to sing. The cables hum in the wind so loudly that the entire span turns into a giant musical instrument. Most people barely notice it, but engineers who hear those sounds instantly know the structure is under stresses it shouldn't be experiencing. Winter turns many cable bridges into deadly ice cannons. Ice accumulates on the cables, and when the temperature rises slightly, huge chunks begin to fall. That's dozens of kilograms of ice hurtling downward at high speed. In some countries, bridges must be closed overnight whenever temperatures cross the freezing point. Otherwise, it becomes a natural bombardment. The problem still has no perfect solution. Engineers experiment with heated cables, aerodynamic fairings, special coatings, but there's still no absolute protection. Sometimes a bridge collapses not because of wind, ice, or even heavy trucks. Sometimes because of people. On the very first day after the opening of London's Millennium Bridge, tens of thousands of people crossed it. And suddenly, the bridge began to sway from side to side, something that absolutely shouldn't happen. But the people didn't know that. Instinctively, they began adjusting their steps to match the bridge's motion, which only amplified the oscillations. A giant feedback loop formed. Bridge sways, people synchronize, swaying intensifies. This is known as human-induced resonance. The bridge had to be closed, and engineers stitched dampers into the structure. Since then, every pedestrian bridge is analyzed for crowd synchronization. But there is an even more subtle, silent killer: metal fatigue. Every passing car, every gust of wind, every temperature fluctuation creates microscopic changes in the internal structure of metal. These accumulate for years, turning into cracks that are impossible to detect with the naked eye. One day, they join together, and the structure loses its load-bearing capacity. This is perhaps the most frightening type of failure: invisible, gradual, and almost unpredictable. Silver Bridge was a suspension bridge over the Ohio River. It collapsed in 1967, taking dozens of lives. The cause was a tiny crack less than 3 millionths long in a suspension component. A short, nearly invisible flaw caused by metal fatigue led to the failure of a single link, and according to the principle of a chain, if one link breaks, the entire system fails. This tragedy shocked the engineering world. It proved that even the smallest defect can bring down a massive bridge. After Silver Bridge, global standards for inspecting suspension bridges were overhauled. On August 1st, 2007, the I-35W highway bridge over the Mississippi River suddenly collapsed. It happened on a normal weekday with hundreds of cars crossing it. The catastrophe was caused by a combination of factors: metal fatigue, corrosion, and overload associated with ongoing repairs. A critical gusset plate lacked sufficient strength and failed, triggering a cascade collapse of the entire structure. Engineers hate this bridge because it demonstrated a brutal truth. Even if a structure performs flawlessly for decades, hidden defects can accumulate silently and reveal themselves at the worst possible moment. This event became a turning point. Bridge inspections across the country were tightened dramatically. Underwater, bridges face a different threat: scour. Flowing water washes away soil around bridge piers, and the foundation loses stability. Sometimes this happens suddenly. After floods, hurricanes, or storm surges, engineers use complex protection systems, but nature still wins occasionally. In 2021, in southern China, one of the spans of a bridge over the Zhujiang River collapsed. Severe flooding lasted for weeks, and the water gradually scoured the soil around a pier. Despite the protective reinforcements, the scour depth exceeded the design estimate. The pier lost stability, and part of the bridge fell into the river. This demonstrated how hard it is to predict soil behavior under extreme weather events, which are becoming increasingly common. For engineers, this bridge is a reminder that hydrodynamics can be just as treacherous as wind and metal fatigue. Water works slowly, but mercilessly. In Japan, bridges are a challenge by definition, because the country lies in one of the most seismically active regions on the planet. But the Okakaki Bridge became infamous not because of an earthquake, but because of a unique combination of climatic factors. Summers in this region are humid, winters are cold, and typhoons frequently pass through in autumn. All of this created an unusually aggressive environment for steel structures. The bridge began to corrode at rates engineers could not predict even in their most pessimistic models. Test steel samples placed near the bridge degraded less than the actual structural elements. As a result, the bridge had to be closed far earlier than its intended lifespan and completely rebuilt. Engineers hate this bridge for one reason: it became a reminder that the real reaction of materials to the environment can never be calculated with absolute precision. Sometimes nature behaves off protocol. These tragedies have become permanent chapters in engineering textbooks. The longer the bridge, the more enemies it has: wind, temperature changes, vibrations, the weight of its own structural elements, shifting soil. Every additional meter increases the risks and reduces the predictability of how the structure will behave. Earthquakes, a special kind of terror for bridges. In seismic regions, a bridge must withstand longitudinal, transverse, and vertical shocks. But the most dangerous phenomenon is soil liquefaction, when solid ground turns into a gel within seconds. Many bridges have been damaged or destroyed precisely because of this, not because of the shaking itself. And corrosion, the eternal enemy, especially in the tropics or near the sea. Salt, humidity, and temperature fluctuations turn metal into brittle powder faster than engineers can repair it. Some bridges need to be repainted every 12-18 months. There are 5 categories of bridges that engineers genuinely fear to build: suspension bridges with extremely long spans, bridges in cold regions, bridges in tropical climates, wooden bridges in real-world heavy-duty operation, architecturally fantasy-like structures. Each of them hides its own unique threats. Why build such bridges anyway? It's a paradox. Engineers know that bridges are dangerous structures. They know that nature will always fight against them, yet they continue to build increasingly complex spans. A bridge is a symbol of overcoming obstacles, of connection, of victory over distance. It is engineering poetry. It is a challenge to the elements. And yes, engineers may hate bridges, but they love them even more.